Welcome you to Kaggle Days San Francisco. My name is Addison Howard. I serve on the Kaggle competitions team. And I'm really excited to present our first speaker here this morning. It's an absolute treat to be able to bring in one of our Grandmasters. You may know him as Idle Speculation. He's been around the Kaggle community for a really long time, even being up to the 4th highest ranking Kaggler we've had on the platform. He's had a lot of success, including most recently winning our biggest prize competition we've had so far in the Department of Homeland Security. He came in first place doing that one. And he's been a part of the community for a really long time. Formerly working for DataLab in Washington, D.C., and is now taking his talents to Palm Beach in Florida with a new job. And we're really excited to have him to present today. As you've seen in your agenda, and as many of you are aware, in Kaggle, cross-validation is sometimes very, very important, if not the only thing that can change your leaderboard ranking, often when that competition concludes. And so we're really excited to have our very own Jeremy Walthers come and speak on how to choose K in your Kfold validation. So please, round of applause for Mr. Jeremy Walthers.
Can you guys hear me? All right. So I've got a really practical talk here, and I guess this slide kind of format represents, it's just, black on white here. Pretty practical talk about how to win Kaggle competitions. So if that's what you're interested in, you're at the right spot. So validation in general is sort of the second most important aspect of machine learning, or modeling, rather. Anybody know what the first most important is? Data. Yeah, data preparation, right? If you don't get your data right, then it doesn't really matter what you do, how you validate, what kind of models you build, doesn't matter. But as far as validation, you want to design your validation in such a way that it reflects how your model is going to be used in practice. And that's going to vary from case to case. A common validation technique is just a train test split, and typically what happens there is you hold out some fraction of your data, maybe like 20% or 30%, and you use that just for validation, and you model on the other part of it. So that technique may not be appropriate in a lot of cases in terms of generalization to new populations which aren't represented in your training set, and also new time periods which are not in your training set. So I just want to say that while I'm going to talk about Kfold cross-validation here, it's not sort of a cure-all method which is going to be broadly applicable to every case. And whatever problem you're working on, you should always try to set up your validation in such a way that it makes sense. So Kfold cross-validation is sort of a souped-up version of a test-train split. And the basic idea is that we're going to do test train splits over and over again and average the results, and in such a way that we're going to increase the sensitivity of our validation procedure at the expense of additional computations. So I just downloaded this off a random web page, but it kind of gives a pretty good idea of what's going on. With your Kfold cross-validation here, you'd be looking at 10 folds. And for each of these folds, you'll do a round where you're going to train a model. See, the first column on the left would be, you'd take the first fold there as your validation set. The other 9 folds would be your training set. You'd build your model on the 9 folds, which are in blue there, and train on the orange set. I'm sorry, did I say train? Validate on the orange set. And you do this for each of those train folds, holding one out. And then you'd get, say, the validation accuracy or whatever metric you're interested in, and you just average those up at the end. So that's cross-validation. So what? Who cares about cross-validation? So I guess I kind of got to motivate why anybody would want to do this. In a lot of cases, a test train split is just going to be good enough, right? You can hold out 20% of your data, and if your data is big enough, then you just look at how it does on a validation set. So in order to try and motivate why we need to do cross-validation, why we need some special techniques here, I want to show you the distribution of the top 10 scores for the Santander competition, which is still ongoing for another couple hours at least. You can, and some of the people who are talking are actually involved in this. Probably they're, at the same time they're talking, they're thinking about what they're going to do, but anyhow. So you can kind of see that I'm making a box plot for every day here. And in the beginning, like some people have some cool ideas. You can see day 6 or so. Some people, those dots are outliers which jump up above the pack. But sort of at the end of the competition, by the time we're entering the last couple days, the distribution of scores is really narrow, right? And the winners of this competition are going to be determined by their difference of score, which is going to be in the 3rd or 4th or maybe even 5th decimal place. And the way they're going to, the way these folks at the top of the competition are going to either succeed or fail is by making decisions which are based on sort of very small differences. So that's sort of a good motivational slide for what I'm going to talk about. So in doing cross-validation or in doing modeling, assuming you just keep going at it, eventually over time you'll have some sort of initial gains at the beginning, and you'll see large rewards from that, but eventually you're going to find that the incremental value that you're adding as you're coming up with new ideas gets smaller and smaller. And eventually, your ideas are going to kind of lie within this band of sensitivity, which you're not really able to detect effectively whether your ideas are working or not. So I guess when you get inside of this band where, say, you could rebuild the same model with a different random seed, and it would tell you something different, you're kind of making decisions purely at random. And making random decisions is pretty much a waste of time. I think you'll all agree. And the worst thing is that a lot of times you may not actually know that you're making decisions at random. So you're going to waste a lot of time pursuing things which probably aren't going to help. What Kfold cross-validation is going to do is going to sort of narrow that band of sensitivity so that every incremental change that you're making, you can kind of track whether that worked or whether it didn't. So now that we agree that there's a need for Kfold cross-validation, there are a couple things we need to discuss about how we're going to choose K. The first thing to consider is there's a trade-off between the number of folds in the computation. So if you're doing Kfold validation, you saw on a previous slide, you want to do 10-fold validation, you've got 10 models to build. And that takes 10 times as long as one model, so there's going to be a trade-off there. Alternately, you could think that, well, if it takes, if it takes as long to build a 50-fold model as 10 5-fold models, you could build 10 5-fold cross-validations and just average the results and probably get something useful out of that. So given a fixed amount of computation we're going to throw at our problem, maybe the next Kaggle competition is going to be like $2 million, and you're going to throw infinite amounts of compute at it. You don't care. And so you want to think, OK, what's the best strategy? And to describe what that strategy might be, I need to go into a little bit of theory. So anybody who's had stats is going to think this is really simple and dull, but a lot of people are probably not going to be familiar with it. I want to think about Kfold cross-validation as being a process which produces an estimator of whatever metric I'm talking about, whatever the metric is for the competition. Maybe it's AUC, maybe it's log loss, maybe it's mean squared error, whatever you have. So this is a process which computes this theta bar thing here. So I've showed in the picture on the right, I'm showing some sort of like bell curve, which is a distribution of theta bars. So how do I come up with a distribution of theta bars? So my thought process is I've got not just my training set, which is some sort of realization of some general process which creates data. So I could have, if I got lucky, a different constellation of the same. That process might generate a different constellation of the same data. And I'm thinking that I'm just generating data sets from a particular distribution, and every time I generate a data set, I'm getting something, some value along this x-axis. So maybe sometimes when I do, I pull out a random data set, I do cross-validation on it, I get an estimate. If I take another, say, data set of the same size, I do cross-validation on that, I get another estimate. And it kind of, if I look at the distribution of those estimates I'm getting this red bell curve that you're seeing here. The blue, I guess the green rather, the green theta is kind of what I'm going to call it the true performance. If I had perfect knowledge of how this thing actually evaluates in the real world, or if you want to think about it this way, it may be the private leaderboard score, that theta. In any case, there's a couple things that I want to point out about this diagram, and they're the bias, which is the difference between the average value of our estimates, which are coming out of cross-validation, and the actual private leaderboard score. And there's also the variance, which doesn't rely on the private leaderboard score at all. It's just sort of the distribution of estimates that I'm generating through doing cross-validation. So I would love to be able to come to this talk and give you guys okay, Kfold cross-validation, the K you need to use is 5, done. Drop the mic, walk out. But it's really not that simple because there's a trade-off between that bias and variance that we just looked at. And so I'm going to say that when you pick K in doing Kfold cross-validation, you should really try and evaluate what you're trying, or trying to firm up what you're trying to evaluate, or try to make sure you know what you're doing or looking for when you do this Kfold cross-validation. So if you just want to do performance estimation, and by this I mean you might want to know how close you are to the other people on the public leaderboard. So the public leaderboard says that other people are coming in at 0.62. If you want to have a very accurate estimate, which is close to that, you're going to want the bias, the thing that you're getting out of your cross-validation to be very close to the theta there. But on the other hand, if you're doing model selection, you're kind of thinking you're generating not just one of these red bell curves, but 2 of these red bell curves, which are close to each other and maybe overlapping. And if they're overlapping, you can think that in the region they're overlapping, you're generating one model which looks very similar in performance to another model. And in that region, you may generate estimates which would be contrary to the actual performance that you'd get on the private leaderboard. So they would be false positives or something like that. But in any case, I think model selection, if you think about those 2 overlapping bell curves, in order to conclude that one model is better than the other, you'd want that variance to be as low as possible. So from a performance estimation standpoint, I can definitely tell you what the right answer, I think I can tell you what the right answer is. Performance estimation, you just want the bias to be as low as possible. So we're in this situation where we're looking on the public leaderboard and we're wondering whether our model is as good as the people up there without submitting. So I think fortunately everybody seems to agree that just increasing K as much as possible reduces your bias. And repeating Kfold cross-validation, as we were kind of arguing there might be motivation for earlier, doesn't really do much for you. So, and the reason for that is because all the estimates all have the same bias. Now, I've got some graphs here, and just look at these a second and try and estimate what year these came from. There's going to be a test on this later. But this is a really old result. It's not really old, but this is from Ron Kohabe's thesis. And this is showing that as you increase the number of folds, the dashed lines, which are the cross-validated estimates to the performance, are approaching some sort of gray bars, which are some sort of 95% confidence intervals that he came up with for the actual or true accuracies. So you can see that pretty much no matter which data set you're talking about, as you're increasing the number of folds, you're reducing your bias. And the negative folds on the right-hand side of this, these are leave 1 out, leave 2 out, and leave 5 out. So this is like Kfold cross-validation with K equal to the size of your data set for -1. So that's performance estimation. It's pretty easy. You just make as many folds as you have the computational capacity for. And since we're at a Google Cloud conference, that could be a lot. You might just take every point in the data set and make that a new fold. As far as model selection, really we're looking for something else here. We're looking for the smaller variance. And assuming that your bias is consistent, sort of the sensitivity of your model selection procedure is just totally determined by your variance. And I'm showing here more graphs from Kohabe's thesis, and these are showing the variance arising from stratified Kfold cross-validation. And if you're wondering whether to stratify in general for cross-validation or not, the answer is you probably should. In any case, you can see some interesting behavior here if you look at the top graph especially. And I'll say that C45 is sort of the prototype for pretty much all the tree-based algorithms that you see these days, so like an XGBoost or LightGBM or anything like that. Before there was any of that, there was C45, and pretty much that's what's sort of the basic underlying component of all those guys. All right, so keep this in mind, and you think that, first of all, think that, all right, if I want to reduce variance as much as possible, increasing the number of folds isn't actually helping, right? If I go up to, say, 20 folds for my vehicle or soybean data, it was actually giving a higher variance than doing 5 or 10. So I'm going to have a process which is actually less sensitive. So just looking at these results, it kind of looks like there's really no reason at all, unless you're doing performance estimation, to go above 10 folds or so. But you might say, well, okay, this is from a long time ago. Everybody have an idea in their mind of how old this is? I think it's actually in the next slide. But actually, it's 2 slides. But in decreasing, let's just fast forward to it, sorry. No, there it is. So Kohabe's thesis was from 1995, but let's go back. So if our goal is really to just decrease the variance of our cross-validation estimates, then you might think that, okay, well, I know how to fit a model, and I know how to do cross-validation. And my favorite cross-validation, or my favorite model building package, LightGBM, it should be XGBoost for everybody here, especially if Bing is listening, or Keras if Francois is in the audience. But your favorite modeling package probably already reports the standard deviation of your metric. And I guess the question you should ask yourself is this useful? And the answer I have for you is it's useful, but, well, I'll just show you. So there's this result from Bengio before he won the Turing Award or got famous for building neural networks or anything. He has this nice paper about the fact that there's no unbiased estimator for the variance of a case-fold cross-validation. So this thing that you're seeing that's being generated by your modeling package, I've said here it's a wildly optimistic estimate, but I guess his result really says that there's no way, okay, I'll say it this way. The estimate is definitely optimistic, and there's no way to know how optimistic it is. That's essentially what he's saying. So it's kind of hard to use this, this standard deviation of the log loss to actually select between models or give any sort of significance to if, say, the difference between your means is so much and that log loss or standard deviation is some, another, amount, maybe you could come up with a z-score out of that. But what this is saying is that z-score is probably not going to be worth using. So that kind of puts us in a bad situation, right? So we are really unable to estimate the variance of a Kfold cross-validation because of his result there, because we have no idea what the bias is. There's no universal variance behavior with respect to increasing or decreasing k. You can see that some of these graphs are flat, some of them are increasing, some of them are decreasing. But that said, if you look at C45, it kind of looks like most of those follow the same trend, at least the ones that you would worry about. The rest are just flat, but they all follow that kind of U-shaped pattern, which if you just assume that that holds in general, you might think, OK, well, looking at this, I'm always going to take 5 or 10. But this is not really telling the whole story. And the reason it's not telling the whole story is because, as I said before, a 2-fold cross-validation takes 1/5 the time of a 10-fold cross-validation, and probably less because the size of your data sets is smaller. So let's look at what happens if we just repeatedly do cross-validation with different seeds. We pick some random test train splits or random folds over and over again. We average the results. What do we get? So one of the reasons why I want to do this is because Kohavi's thesis is 25 years old, so maybe the stuff that he was doing in there is no longer reflective of what we do today. Another reason is because I wanted to actually show, in terms of computation, how good or bad of an estimate for variance am I getting, or what the impact on the variance is, rather. And yeah, so in terms of just, if you don't care about the compute at all, and you're just willing to do k-fold cross-validation for any particular k over and over again, you can kind of see from this graph that it looks like, I guess I don't really have the x values mapped out precisely, but it definitely looks like a low value of k is best, right? And that may be a little counterintuitive to think that, like, OK, I mean, I could do, I'm only using half the data and building a model on that. But if I'm doing this so many times and I'm generating estimates which are less dependent, because you think if you're using most of the data to fit your model every time, the models you're building are going to be very similar. And they're not going to really reflect maybe the differences which may have occurred on a different data set. But in any case, the shade in this graph is giving the amount of computation. You can see that you can get down really far here with 2-fold validation, surprisingly far. And if you're going to do this with 100-fold validation, it's going to take you a lot of compute, and you're not going to get as good of results, at least in terms of variance. So let's go on. The next, this is just a similar sort of graph, except with a different competition. The last one's from Microsoft malware competition. This one's from the Santander 2019 challenge, which is still ongoing. And the way I'm generating this is I'm just taking 10,000 records. Right? I'm splitting the data set into chunks of 10,000 records, running a k-fold cross-validation on that. And for this particular competition, there are 200,000 data points or records, so we can do this 20 times, and then we get the standard deviation from that just by averaging for those 20 trials what the, I guess it's AUC was here. So these results generally mirror what Kohavi had in his thesis for C45, and that if you're looking initially up towards the top where we're not spending, or we're spending the minimal amount of computation, if we're just doing these once, we get kind of this U-shaped. If you're looking just at the top edge of this graph, we get this U-shaped behavior where we're probably better off taking 5 or 10. But if we're going to allow ourselves to repeat k-fold cross-validation over and over again, then it's probably better to just take 2 or 3, which may be surprising to some people. It was surprising to me when I looked at this. So when I look at this and I think, okay, well, I mean, that's great in theory. You've got this theory about variation. You've got this theory about bias. Does it really work? So does it actually work? And the variance from cross-validation could arise from a variety of sources. You could have data resampling outliers, the fact that you're rebuilding models, the sensitivity of your metric. And does any of these results that we're coming up with show anything tangible? And here you're seeing, I guess I should mention where this elbow is in the curve for this particular problem. That 10, I've sort of scaled this so it's 100% compute, but the 10 is really doing twofold cross-validation 30 times. So if you want to have some idea of how many times you want to repeat, that could be a guideline. But in terms of figuring out whether K actually works, I want to do a concrete example of variable selection. And sort of in general, if you're building a tree-based model, it's easy to figure out if the top variables are important, and less easy to figure out if that variable down in spot 20 or 30 is actually important. So this test or trial that I set up was I just took the top 50 attributes out of that Santander competition. Then I took attributes which were in places 51 through 100, and I compared that to attributes which were generated completely randomly. So I make fake attributes which are drawn from a uniform distribution. For whatever reason, some models are going to pick those. So in this trial that I'm doing here, I'm doing Kfold cross-validation over and over again. And I'm doing I'm doing this twice. So I've done it once with the real variable and once with the random variable. And then whichever one had the better log loss, I would pick that. Not necessarily the one which I knew was the correct one, but whichever one was better through the cross-validation technique. So what you can see here is that if I'm doing 100-fold cross-validation, I'm just getting a result which is slightly better than random at variable selection. Whereas if I'm doing, by slightly better than random in this trial, you've got 50 random variables versus 50 non-random, you're going to get 50% of the time, you're going to be right. But down at twofold or threefold cross-validation, the success rate for this thing is up over 80%, which seems crazy to me, but it's real. So I just want to impress upon you that this is extremely powerful and extremely useful. But does it actually work, right? So I gave you sort of the best possible view of this. Now I'm going to give you the other view. So what I want to say here is that in that particular model selection problem, it does work really well. But if I look at another application, it may not work as well. So the reason is that larger training sets have a higher capacity for model complexity. So if I'm doing, remember that we're in Kfold cross-validation, we're splitting our data into K parts. So if we're splitting it into 2 parts, we're essentially giving up half of our training data. And you could think that if I'm giving up half of my training data, I'm not going to be able to build as complicated of a model without overfitting. And that's definitely going to be a problem. So here, instead of looking at variable selection, I'm looking at picking the number of rounds that I want to use through cross-validation. And down along the bottom, there's a K. So you can see that if I'm using twofold cross-validation, it doesn't matter how many times I average it. It's always going to tell me that I should use 200 less than the optimal. So why is that? You might say that our estimate for the number of rounds that we're going to use is biased, but I wouldn't really phrase it that way. I would argue instead that we're in a situation where we have inconsistent bias, and we're trying to select between models with inconsistent bias. So, and in the graph on the right, you're seeing actually the blue line is the cross-validated estimate, and the red line is the actual. So the difference between the two is the actual bias from doing this cross-validation. You can see it's increasing over time. So I want to say that low K works in the sense that as long as you're in a situation where your estimates have comparable bias, it's extremely powerful. So back to what you should choose for K. Now, I think the first time I wrote up this slide, I actually put some numbers in here. I took those numbers out because it really depends. It always depends on your data, and you should always look at what your data is. But there are differences in when you'd want to choose in each of these categories. For high K, if you want performance estimation, mid K, you're doing some sort of parameter tuning. I would say mid K there for a couple of reasons, in that you don't want to expend tremendous amounts of compute just tuning parameters. For low K, this is generally where you're going to have comparable bias in situations where you know you have comparable bias, as in our variable selection problem. And as always, I've got a list of caveats on the left saying that, essentially that every problem is different, and these Kfold cross-validation or any sort of complicated validation doesn't really matter so much as the size of the data increases. Then you should probably at some point just use a random test train split, assuming that makes sense. So this whole time I've just been talking about GBMs, really. There are hundreds of other types of models, and I wanted to just say something about this because I haven't said anything else about neural nets or linear models or factorization machines. But generally speaking, for simpler models on well-behaved data sets, you expect that both the variance and the bias decrease as the number of folds go up. And at the same time, I want to say, unfortunately, we're typically not interested in fitting those types of models because the performance isn't such that it's worth it, at least for a Kaggle competition. So I went 30 seconds over, but thank you.